Hi, my name is Rebecca Fath, and this is my lab of motion of falling objects. The objective of this lab was to compare the change in position and velocity of two objects when one falls slowly and one falls quickly. We wanted to really observe the drag force. My two examples was I used a full water bottle and I used an empty water bottle that was crushed up. As you can see, the crushed up water bottle only fell 0.207 meters in 0.33 seconds, whereas the full bottle fell 0.542 meters in 0.33 seconds. This is because even though they both had the same gravitational force acting on them, they have different forces of drag acting on them. When there's no drag force, we set this to equal to 0. That means that the force of drag will also equal 0 because it's times this constant, and we only have gravitational force. However, when looking at our data, we can see the red line being the no drag, that this cannot always be used because obviously the data points are very different for our tracker data, and that's because we have to include the force of drag. Over here in the full bottle, we can see that drag did not have as large as an impact on the bottle, but you can still see that there is some force of drag there, making the data points a little off. So we looked at the data and we had to come up with a constant that we can multiply by the velocity vector in order to find out how much effect drag had in order to give us a better fit. So for the crushed up water bottle, I ended up finding a constant of 6.65 to multiply by the velocity vector, which is again in the opposite direction of the motion, and then this drag will be added to our net force in order to show how it was acting on it. You can see here that the force of drag was very large and is almost canceling out with the force of the gravitational. However, if we did show the drag force of the full water bottle, we can't even see that arrow because it's so small, but it still has some impact on it, and that's where we get these graphs where you can see here the drag force showing from our Python, and then here again making it a much better fit for our blue lines. So here we see this drag force acting, and it's a little different from here, because here we can see that it's reaching some terminal velocity. This is our what if question, or what does it mean question. So terminal velocity is when the gravitational force and the drag force end up canceling out and equaling to 0. When this happens, we reach a terminal velocity, which is our max velocity, which will continue to go all the way to the ground. So that's when we get this velocity, and you can see it's a very linear line, which means that the velocity will be constant. Over here, we do not reach a terminal velocity. You can see kind of close, we're kind of getting closer to it, but it's still, the slope isn't very constant, so the terminal velocity wasn't reached there. What if we added initial velocity? What would happen if we added initial velocity? Let's see here. We're going to add a little larger drag force, and we're going to add initial velocity, -1. So when we add initial velocity of -1, what happens is that with this, if we just throw it to the ground, we've already given it velocity, is that the terminal velocity is going to be met faster, because we are showing that when there's already velocity added to it, this drag force is already larger, and then it's getting closer to the force of the gravitational force here. So thank you for watching my lab. Have a great day.